Hello and welcome, esteemed researchers and fellow academics attending the 4th International Euro-Asian Conference on Science, Engineering and Technology. I'm Mohammed Janani from Istanbul Gelishim University, Faculty of Engineering and Architecture, Department of Electrical and Electronics Engineering. Today I would like to present to you a presentation on the design and implementation of a temperature and SpO2 detection device using the Atmega 328P chip for COVID-19 patients. Introduction. What is SpO2? Blood oxygen saturation, also known as SpO2, is the fraction of oxygen saturated hemoglobin relevant to the total hemoglobin, unsaturated and saturated in the blood. And it is also the measurement of how much oxygen your body is carrying as a percentage of the maximum it could carry. Where a very precise and specific balance of oxygen in the blood is necessary to keep the body functioning properly. For a healthy individual, the normal SpO2 should be between 94 to 99%. High altitudes and other factors may affect what is considered normal for a given individual. If the patient has a measurement of less than 90%, action must be taken. During the past decade, there has been rapid growth in advanced health monitoring techniques to assist healthcare professionals in more accurately monitoring their patients. Coronavirus disease COVID-19 is an infectious disease caused by the SARS-CoV-2 virus. Most people infected with the virus will experience mild to moderate respiratory illnesses and recover without requiring special treatment. On the other hand, some will become seriously ill and require medical attention, which may lead to death if not treated. Some recovered patients may suffer from blood clots, which may lead to cardiac arrest. Pulse oximetry measures the oxygen saturation in the blood. Here we aim to design a non-invasive diagnostic device to improve the SpO2 measuring techniques by using the Atmega 823P microcontroller chip. Materials and methods. A microcontroller-based electronic circuit was designed and implemented with non-invasive medical sensors to measure the SpO2 of the individual. The microcontroller used is an Atmega 328P, which is a low-power CMOS single chip with an 8-bit processor core. By executing powerful instructions in the single clock cycle, the microcontroller achieves throughputs approaching 1 Mbps per megahertz, allowing the system to be optimized for power consumption versus processing speed when high performance isn't needed. The Atmega 328P works at 5 volts and with the smallest possible quantity of components like a 22 picofarad capacitor and a 16 MHz crystal oscillator. When combining it with the microcontroller, will make it run without problems. In our design, we used two sensors, the MAX 3100 and the MLX 9614, to measure oxygen saturation and the body temperature respectively. We also used the ESP 8266 to provide wireless connectivity for the device. The first sensor is the MAX 3100, used to measure the oxygen saturation level in the blood of the individual. It combines two LEDs, a photodetector, optimized optics, and low-noise analog signal processing to detect pulse oximetry and heart rate signals. It uses red and infrared lights, which are propagated from the LEDs, reflected off the blood veins, and received on the photodetector. The second sensor was the MLX 9614, a non-contact infrared temperature sensor with the ability to obtain two readings, The first being the object temperature and the second is the ambient temperature. It has a built-in optical filter which filters visible and near visible light, eliminating temperature changes which caused by ambient light and sunlight, reducing their effect on the measurements. It is small in size, low in cost, easy to integrate, with factory calibrated in wide temperature range from -40 to 125 centigrades for temperature sensors and -70 to 380 for object temperatures. The measurements were displayed on a built-in OLED 1-inch screen or a 2-line 16-character LCD module with I2C interface. While the device will be part of the Internet of Things, it will connect to the Internet via the ESP8266 Wi-Fi module. This module will give access to the Internet. This Wi-Fi module is a self-contained SoC with integrated TCP/IP protocol stack that can give the microcontroller access to the Wi-Fi network. The data is collected by the sensor, then processed by the Atmega microcontroller, while the final information is accessed by either a digital OLED screen connected directly to the electronic circuit, or by using a smartphone or computer to access the ThinkSpeak website, where the measurements are accessible. The ThinkSpeak website is a free analytical platform service, which allows you to aggregate, visualize, and analyze live data streams in the cloud. A device containing the MAX 3100 and the MLX 9614 sensors was designed, and non-invasive measurements were taken from 17 patients. While the device was tested on several patients from different ages and was compared to a generic SpO2 measuring device with no temperature sensor, the results were very accurate when compared to a medical-grade measuring device used in medical facilities. The results were almost identical to that of a high-level medical device and had much better accuracy than the generic devices found on local shops. From the table, we can see that the SpO2 readings for patients 1, 4, 9, 12, and 17 show a lower accuracy rate when compared to the Atmega device, and for patients 5, 6, and 13, 14, the generic device had the same readings for both the patients. The data collected was sent to the ThinkSpeak website for remote real-time viewing after creating channels for different measurements and assigning them to each patient. Our conclusion: a diagnostic, non-invasive wearable system is designed to continuously monitor the SpO2 measurement and temperature of COVID-19 patients. This system is designed to be used by COVID-19 patients and recovered COVID-19 patients, where blood clots are long-time effects of recovering patients and can be detected by the use of SpO2 measurements. The device is low cost, small in size and weight, with minimal power consumption. It has the ability to measure the SpO2 saturation levels with high accuracy and measure body temperature, providing remote real-time monitoring via connection with the Internet, making it part of the Internet of Things. It can be considered point-of-care testing device, which will eliminate the need to visit medical facilities. Thank you all for your participation.